Hello everyone, this is Bandgar SS working as an assistant professor at Department of Physics, KTHM College, Nasik. Today we have to going to discuss TYBSc paper 4 Advanced Electronics. Today we have to going to discuss the first chapter of sensors. So starting with first concept, metal resistance versus temperature device. The primary method for measurement of temperature sensing device is change in electrical resistance of that material. Example like as a RTD, that is the resistance temperature detector. A metal is an assemblage of atoms in the solid state in which the individual atoms are in a equilibrium position with superimposed vibration induced by thermal energy. The characteristics of metal is the fact that each atom gives up one electron is known as valence electron, and they are freely moved throughout the material and it becomes a conduction band. The whole material conduction band, electron and valence band overlapping to each other in energy band of metal. The material exhibits a resistance to electrical current flow which is a function of the vibration of atoms with greater amplitude and frequency. Now this diagram shows the metal resistance versus temperature devices. So there we have to know the two metals are used, nickel and platinum, and it varies their temperature and you will get their resistance. So it is the near about linear but actually not linear. We know resistance is directly dependent on length and the cross-sectional area of the conductor given by R is equal to rho L upon A. There is the temperature is constant. Rho is the resistivity of the metal, ohm per meter. Then L is the length of metal, that is the meter. A is the cross-sectional area, that is the meter square, and R is the sample resistance in ohm. So we can get the analytical approximation R upon R 55 degrees Celsius, rho T upon A, so the R is the 55 degrees Celsius upon A, rho T upon R 55 degrees Celsius. So that is the room temperature. So you will get the resistance versus temperature. Now next one is the linear approximation, an equation for a straight line that approximate a resistance versus temperature, that is the RT curve, over a same specified span. So we have to define some temperature span and measure the related resistance of the metal. So you will get the linear approximation. So RD is equal to RT0 in bracket 1 plus alpha 0 change in T, change temperature. So that is the T1 to T2. So RT is linear approximation of resistance at temperature T, RT0 resistance at temperature, initial temperature T0, and change in temperature T minus T0. And alpha 0 is a fractional change in a resistance per degree of temperature. So alpha 0 is equal to 1 upon initial temperature RT0 into R2 minus R1 upon T2 minus T1. So you will get the degree of temperature. So that graph shows the linear approximation of resistance versus temperature between T1 and T2, or initial temperature or maximum temperature. Now next concept is the resistance versus temperature approximation, that is the quadratic approximation. So the quadratic approximation to the RT curve is a more accurate representation of the RT curve over some span of temperature. It includes both a linear term before that varies the square of the temperature, such as analytical approximation is. So RT is equal to RT0 in bracket 1 plus alpha 1 del T plus alpha 2 del T square, bracket complete. So here RT is the linear approximation of resistance at temperature T, then RT0, that is the resistance at temperature T0, alpha 1 linear fractional changes in resistance with temperature, del T is equal to T minus T0. Alpha 2 is equal to quadratic fractional change in resistance with temperature. Now next concept is the resistance temperature detector, that is the RTD. So what is the principle of RTD? The RTD is a resistance temperature detector that operates on the measurement principle that a material's electric resistance changes with temperature. As temperature increases, the resistance increases, and vice versa, means temperature decreases and resistance decreases. The RTD element is made from a pure material like as a platinum, nickel, copper, gold, silver, tungsten and aluminium, and it has the high accuracy, high sensitivity, low drift, high chemical inertness, long-term stability, linear characteristics over a wide range of platinum resistance thermometer, advantages preferred than other materials. So mostly we have to use a platinum temperature detector. So platinum thermal resistance, that is the PTR, is same operating principle of a resistance temperature detector which uses platinum for determining the temperature. Various metals and their temperature response with related resistance. So here we have to use nickel, copper, platinum with respect to temperature, and you will get their resistance. So resistance of conductor or metal is given by R is equal to rho upon L upon A. T is constant. So R is the resistivity of material, ohm into meter. L is the length of the meter, and A is the cross sectional area of the meter, that is the meter square. R is the sample resistance, it is the ohm. The principle increases in resistance due to change in resistivity of the metal with temperature. So we have to use a different materials, platinum, copper, nickel, tungsten, iron, aluminium, and their temperature coefficient, that is the alpha, and their operating temperature range. So platinum has the minimum temperature coefficient and it has the many advantages, so that's why we have to use mostly RTD as a platinum resistance temperature detector, that is the PTR. Now platinum resistance thermometer. So see the diagram, it is the construction of the PRT, platinum resistance thermometer. So a typical construction of PRT, where a platinum metal wire is wound on the grooved hollow insulating ceramic former and covered with a protective cement. The end of the coil are welded to stiff copper leads that are taken out to be connected in one of the arms of the Wheatstone bridge. For fast response, the arrangement can be used directly in the medium. However, in most applications, a protective metal sheath is used to provide rigidity and mechanical strength. Using platinum fabricated thin pins on a substrate which have advantages of a extremely low mass, consequent more rapid thermal response. The resistance of wire of platinum is measured by passing a current through it and measuring the voltage across it with a suitable voltmeter. Now next concept is what is the disadvantages and application of RTD. So their disadvantages are low sensitivity, it is the expensive, error due to shock, acceleration, contact resistance, then slow response, large size, high cost, possibility of self-heating, bridge circuit required for single conditioning, and their application laboratory and industrial precise. Now next concept is the resistance temperature detector, that is the RTD. So their characteristics, first characteristics is the sensitivity, the linear fractional change in resistance with temperature. So how to change the temperature? There changes in a resistance, that is the linear fractional change. First one, platinum, it is the 0.004 per degree Celsius, and nickel 0.005 per degree Celsius. Only change in 0.4 ohm would be expected for a 100 RTD if the temperature change by 1 degree Celsius. And second one is the response time. If RTD has response time 0.5 to 5 seconds or more, the slowness of response due to principally to the slowness of thermal conductivity is bringing the device into thermal equilibrium. If poor thermal contact, it is a slow response. If good thermal contact, it gives the fast response time of RTD. Now, next characteristics of RTD is the signal conditioning. So we have to use a bridge circuits or compensation lines, differential amplifier. So bridge circuits are used for very small fractional change of resistance with temperature. The compensation line in the R3 leg of the bridge is required when the lead lengths are so long that thermal gradients along the RTD leg may cause changes in line resistance. These changes show up as false information and suggesting changes in RTD resistance. By using compensation line, the same resistance changes also appear on the R3 side of the bridge and cause no net shift in the bridge circuit. Next characteristics of RTD is the dissipation constant. The RTD has a resistance. This is a I square R power dissipated by the device itself that causes a slight heating effect, that is the self-heating. To avoid self-heating, then must be kept current low and constant. The dissipation constant shows that I square R power losses in the RTD equal to 25 milliwatt, then the RTD will be heated by 1 degree Celsius. The dissipation constant is usually preferred to condition. First one is the free air and second one is the well stirred oil bath. The capacity of medium to carry heat away from the device. The self-heating temperature rise can be found from the power dissipated by the RTD and the dissipation constant form. So del T is equal to P upon PV. So where del T is the temperature rise because of self-heating in degree Celsius, P is the power dissipated in the RTD from the circuit in watt, and PD is the dissipation constant of the RTD in watt per degree Celsius. Now, next one is the in contrast to metal, electrons in semiconductor materials are bound to each molecules with sufficient strain that no conduction electron are contributed from the valence band to the conduction band. The energy gap Wg exists between valence and conduction band. When T is equal to 0 Kelvin, the more energy gap del omega G of material insulator, there is no thermal energy. When temperature increased, then molecules begins to vibrate, which provides energy to valence electron. When energy equals or exceeds the gap energy del omega G, these electrons becomes free from the molecules which are in the conduction band and is free to carry current through the bulk of the material. Further temperature is increased, then more and more electrons gain sufficient energy to enter conduction band. Then semiconductor becomes a good conductor of current. Next one is the semiconductor resistance versus temperature. So here we have to use a semiconductor material, resistance versus temperature. So temperature is changes with their semiconductor material resistance are changes. In semiconductor behavior, changing their energy gap by using temperature. When the material is heated, then this passes from insulator to conductor. The semiconductor energy gap generally del G 0.001 to 4 electron volts. So that is the 1 electron volt is equal to 1.6 10 raised to minus 19 joule. The thermal energy of molecule, that is the WTH, is equal to 3 by 2 kT. So where K is the Boltzmann constant and T is the temperature. So for 0 Kelvin, Wt is the 0.0 electron volt. When it is the 100 Kelvin, WTH is a 0.013 electron volt, and T is equal to 300 Kelvin, WTH is equal to 0.039 electron volts. So that diagram shows their temperature and resistance response of a semiconductor material. Now next concept is the thermistor. A thermistor is a type of resistor that used to measure temperature. It measures temperature through changes of resistance. It usually negative temperature coefficient, which means the resistance of the thermistor decreases as the temperature increases, and vice versa. So thermistor resistance is increases when temperature is the decreases. Thermistor characteristics are very different from those of RTDs and depend on the peculiar behavior of semiconductor resistance versus temperature. Thermistor characteristics is a non-linear. The changes in thermistor resistance and its desired temperature has inversely proportional relation between them. Next concept is the thermistor characteristics. Starting with first characteristic, sensitivity. It is the important factor in their application. Changes in resistance change in temperature 10% per degree Celsius. The thermistor 10 kilo ohm may change 1 kilo ohm for 1 degree Celsius change in temperature. Null detecting bridges circuits are used to provide large sensitivity for control less than in 1 degree Celsius temperature. Second one is the construction. The thermistor is a bulk semiconductor, many forms fabricated, like as it includes discs several centimeter, beads 1 millimeter, and rods which are several centimeter thick, and wide range of resistance values at any particular temperature, which depend on variation of doping and use different semiconductor material. Next characteristics is range. The temperature range of thermistor depend on the materials used to construct the sensors. There are three range limitation effect. First one, the melting and deterioration of the semiconductor, deterioration of encapsulation material, intensity at higher temperature. If temperature is lower, -50 to 100 degrees Celsius, the resistance increase into mega ohm. If temperature upper 300 degrees Celsius, then resistance decreases into ohm. Thermistors unable to measure temperature effectively because very little change in resistance occurs. Mostly thermistor encapsulated in plastic, epoxy, Teflon, and inert material. Now next characteristics of thermistor is response time. If response time of thermistor depends upon the quantity of material present and environment. For smallest bead thermistor, an oil bath 1/2 second with good thermal contact, and air, that is the 10 seconds. So with poor thermal contact. When thermistor is encapsulated by material which protect against hostile environment, and response time thermistor is increased in an air environment. Large disc or rod thermistor may have response times of 10 seconds or more, even with good thermal contact. Next characteristic is signal conditioning. Because of thermal exhibits such as a large change in resistance with temperature, thermistor have a non-linear features, then so a bridge circuit is used for fractional changes of resistance with temperature, which is difficult to measurement. Actually, resistance of thermistor which decides or limits the power dissipation or interference with the environment for which temperature is being measured. Dissipation consists of thermistors in milliwatt, power required to raise temperature above its 1 degree Celsius environment. The dissipation constant for an free air 1 to 10 milliwatt per degree Celsius, and for an oil bath more than 10 milliwatt per degree Celsius. Now next concept is the thermocouple. It is a device that measures temperature on the basis of thermoelectric principle is known as thermocouple. Thermocouple is two metals are coupled together basis on electric and thermal properties of different metals. There exists another dependence of electrical behavior of material on temperature that forms the basis of a large percentage of all temperature measurement. This effect is characterized by a voltage generating sensor in which an motive force EMF is produced that is proportional to temperature, such as EMF is found to be almost linear with temperature and very repeatable for constant materials. The thermocouples are thermoelectric transducers which are most commonly used in electric device for temperature measurement. Its operating principle that a current flows in a closed circuit made up of a different metals. If the junctions of the two metals are kept at a different temperature, the thermocouple is a temperature transducer that develops an EMF which a function of the temperature between hot junction and cold junction. The construction of thermocouple is two different metal wires twisted, braced, welded together, with each wire covered with insulation, either magnesium oxide mineral insulation for normal duty or ceramic insulation for heavy duty. The thermocouple principle mainly depends on the three effects, namely SEEBECK effect, Peltier effect and Thomson effect. So starting with first effect, SEEBECK effect, it is the temperature difference between two different metals induce the potential difference between them. When the heat provided to any of the metal, the electron starts flowing from hot to metal to cold metal. This is direct current induced in the circuit. The two different metals A and B are used to close loop with connecting junctions at temperature T1 and T2. The EMF produced is proportional to the difference in temperature between two junctions. Next, SEEBECK effect. The SEEBECK coefficient or sensitivity S is equal to E upon T is equal to A plus BT plus CT square, where T is the change in temperature, E is the generated EMF, A, B and C three constant value of reference temperature due to major EMF. The EMF induced in the thermocouple circuit and is given by the equation E is equal to alpha T plus beta T square and E is equal to alpha T2 minus T1, where T1 and T square T2 is equal to temperature difference between the thermocouple hot and reference junction, and alpha and beta are constant which is independent on temperature. Next one effect is the Peltier effect. The Peltier effect is the inverse of the SEEBECK effect. The Peltier effect states that the temperature difference can be created between any two different conductors by applying the potential difference between them. A closed loop of different metals A and B when an external voltage is applied to the system to cause a current to flow in the circuit. Because of the different electrothermal transport properties of metals, it is found that one of the junction will be heated and other cooled, like as a refrigerator. Next, types of thermocouples. The types of thermocouples classified what type of metal used in thermocouple, which decides the sensitivity, accuracy and range of the thermocouple. The following table gives the different types of thermocouple and their composition, range and accuracy. So we have to know these types of thermocouple, like as a J type, K and N, T, E, S, R and B, and their combination and their range and their accuracy. Now next concept is the advantages, disadvantages and application of thermocouple. So starting with advantages, it has the high accuracy, it is the robust, can be used in environments like harsh as well as high vibration. Thermal reaction is very fast. Operating range is wide operating temperature range. Cost is low, extremely consistent. Disadvantages, it is gives non-linearity, least stability, low voltage, reference is required, least sensitivity. Thermocouple calibration is hard. Now application, it is used in temperature sensor, in thermostat, in office, home and businesses. It is also used in industry for monitoring temperature of metals like as iron, aluminium and etc. This is used in food industry for cryogenic and low temperature application. The thermocouple are also used in heat pump for performing thermoelectric cooling. It is also used to test temperature in chemical plants, petroleum plants. It is also used in gas machine for detecting for pilot flame. Next concept is the thermocouple polarity and tables. The thermocouple polarity is decided by the reference junction temperature TR and measurement temperature is the TM of two metal wires. The example IR constructed is minus 210 to 760 degrees Celsius. If TR is 0 degrees Celsius less than TM is 100 degrees Celsius, then thermocouple output is plus 5.27 millivolt, which is gives ion is more positive than concentrate. If TR is 0 degrees Celsius greater than TM is minus 100 degrees Celsius, then thermocouple output is minus 4.63 millivolt, which gives ion is less positive than concentrate. The thermocouple measured voltage at TR and TM, but practically measured voltage does not fall exact on the table value. So it is necessary to interpolate between table values. The desired value of temperature can be where TH and VH is higher temperature and voltage, TL and VL lower temperature and voltage, and VM is the measured voltage. So TM is equal to TL plus TH minus TL upon VH minus VL into VM minus VL. Next concept is the thermocouple characteristics. To establish a definite relationship between to provide output measured EMF of the thermocouple, that is the with respect to temperature, TM is exposed to the environment whose temperature measured with junction is formed of metal A and B. TR is two other junctions formed to common metal C which connects to measurement apparatus. It is known as TR. The voltage produced has magnitude dependent on the absolute magnitude of the temperature difference TM minus TR, and also a polarity dependent on which temperature TM and TR. Use the extension wire of reference junction temperature TR for measurement of remote location without upsetting the measurement process. So the first diagram is the 3-wire thermocouple system, and when we use the extensive mode, so that time that is the B diagram of the thermocouple. Use of extension wire in a thermocouple system. Now next one is concept is the thermocouple characteristics. First one is the sensitivity. The sensitivity strongly depends upon the type of signal conditioning employed and on the thermocouple itself. The TC voltages less than 100 millivolt, example type J is 0.05 millivolt per degree Celsius and type R is 0.006 millivolt per degree Celsius. And construction, it is the simply a welded and even twisted junction between two metals. It is the sheath, a protective covering or oven seal in a glass or protect unit from a hostile environment. From the size of TC, 1 in rugged environment 10 to 30 AVG wires, and in refined biological measurement it is the 0.02 millimeter micro. And third is the range. Thermocouple has greatest range, example J is equal to minus 210 to 760 degrees Celsius, and S is a minus 50 to 1480 degrees Celsius. Next characteristic is time response. The time response of the thermocouple is depend on the size of wire, protective material used for thermocouple. It is a time response equates to how long time for thermocouple to reach thermal equilibrium with the environment. It also depend on the good thermal contact, poor thermal contact. Example, one thick wire stainless steel sheath, it is the 10 to 20 second high time constant, and small gauge wire, it is the 10 to 20 millisecond, it is the low time constant. Next concept is the signal conditioning. The thermocouple has output voltage very small, typically less than 50 millivolt. Small signal easily affected by electrical noise, so that signal required amplification. Thermocouple is used with a high gain differential amplifier. Next characteristic, reference compensation. We know that the thermocouple output voltage is proportional to the difference between TM and TR. The variation junction temperature TR as directed errors in the measurement junction temperature TM determination. The following techniques are employed for reference junction compensation. First one is the control temperature reference block. The control room has temperature control box which precisely control reference temperature are regulated. The thermocouple are in use. Extension wires bring all reference junction to a temperature control box in the common room. Readouts of temperature from the thermocouple voltage takes into account. This is known as the reference temperature. The second concept is reference compensation circuit, a specialized IC used to add or subtract the correction factor directly to the thermocouple output. The IC is actually temperature sensors which measures the reference junction temperature and includes circuitry that provides a scale correction voltage depending upon the type of IC being used, which is known as cold junction IC point compensator. IC temperature is the reference temperature, and third one is the software reference correction. In computer-based measurement system, reference junction temperature necessary correction provided by the software when the reference junction temperature measured by a precision thermistor or IC which provided as input to the computer. Next characteristics is a noise, that is the unwanted electrical signals. We know that thermocouple output voltage is very small, less than 50 millivolt. So that is easily affected by noise. So in the industrial environment, electrical machines generated electrical noise up to 100 millivolts. So a thermocouple constitutes an excellent antenna to pick up of noise from electromagnetic radiation in the TV, radio and microwave band. So thermocouple may have many times more noise than temperature signal at given time. So these two precautions are carried out. So first one is the atomic reference correction is now common in thermocouple system. Frequently thermistor or other solid state temperature sensor are used as a reference measurement. And second one is the thermocouple voltages are small. Greater care must be taken protect against electrical noise by using shielding, twisting and differential amplification. Now next concept is the noise reduction techniques of thermocouple. The extension or lead wire from the thermocouple to the reference junction or measurement system are twisted and then wrapped with a grounded foil sheath. The measurement junction itself is grounded at the point of measurement. The grounding is typically to the inside the stainless steel sheath that covers the actual thermocouple. An instrumentation amplifier that has an excellent common mode rejection is employed for measurement. The differential amplifier must have very good common mode rejection to add noise rejection process. Equal voltages are induced in each loop of the twisted wire but of opposite phase, so they are cancelled. Temperature sensors are bimetal strips. So it depends on the concept of the thermal expansion. When greater the thermal energy causes the molecules of solid to execute greater amplitude and higher frequency vibration about their average position. It is the natural to expect that an expansion of the volume of a solid would accompany this effect, as the molecules tend to occupy more volume on the average with their vibration. This effect varies in degree from the material because of many factors like as the molecular size and weight, lattice structure and so on. This is a volume expansion means length expansion of solid or metal in the terms of rod or beam. L is equal to L0 in bracket 1 plus alpha del T. So there is the alpha is thermal expansion of metal, del T is equal to T minus T0. L0 is the initial length or rod length at temperature T0. Now how to work that bimetallic sensors and what type of material we have to use and their thermal expansion coefficient. aluminium, copper and steel, and their thermal expansion coefficient. So a bimetallic strips used to convert temperature change into a mechanical displacement. The strips consist of two strips of two different metals which expands at different rates when they are heated, usually steels and coppers, in some cases steel and brass. The different expansion force the flat strip bend one way if heated. In the opposite direction is cooled below its initial temperature. The metal with higher coefficient of thermal expansion is on the outer side of the curve when the strip is heated and on the inner side when cooled. The sideways displacement of the strip is much larger than the small lengthways expansion in either of the two metals. A gas thermometer is based on the basic laws of gases. A gas is kept at constant volume and the pressure and the temperature vary. The ratio of gas pressure and temperature is constant. P1 upon T1 is equal to P2 upon T2, where P1 upon T1 absolute pressure temperature in state 1, P2 upon T2 is absolute pressure and temperature in state 2. Gas thermometer converts temperature information directly into a pressure signal which converted into an electrical signal. The gas most commonly employed as a nitrogen. Time response is slow in relation to electrical device because of the greater mass that must be heated. Then applications are pneumatic system, analog and digital process control. Now next concept is the vapor pressure thermometer. So it gives the relation between the temperature and vapor pressure, and it gives the characteristics. The vapor pressure thermometer converts temperature information into pressure, operates by different process. If closed vessel partially filled with a liquid, then the space above the liquid will consist of evaporated vapor of the liquid at pressure depends on the temperature. If the temperature is raised, then more liquid will be vaporized and the pressure will be increases. If the temperature is down, then condensation of the sum of vapor and the pressure will be decreases. Due to liquid and vessels must be heated, range is limited and response time is slow, 20 or more seconds. It represented as del P upon del T is equal to P2 minus P1 upon 2 minus T1. Next concept is the liquid expansion thermometer. A liquid has shown an expansion in volume with temperature. For temperature measurement, the liquid in glass thermometer following relationship govern the operation of the device is Vt is equal to Vt0 in bracket 1 plus beta del T. Del T is equal to T minus T0. So Vt and Vt0 volume at temperature T and T0. Beta is the volume thermal expansion coefficient. For liquid expansion of glass container must be used to obtain high accuracy in temperature indication, mostly not used in a process control system because of it required to convert temperature into an electrical signals. Next concept is the solid state temperature sensor. So it shows the diagrams, Zener diode, resistance, and we have to bombarding temperature on Zener diode, and you will get their output voltage. A solid state temperature sensor which offers voltage that vary linearly with temperature over a specified range. At room temperature 20 degrees Celsius to 93 Kelvin, Vout is equal to 3.516 volt. Such as exploding temperature sensitivity, doped semiconductor devices such as diode and transistor, Zener diode in which the Zener voltage increases linearly with temperature. Due to self-heating problem of Zener diode, power dissipation is more and accuracy is less. If increasing the value of resistor up to 2K, then minimize the power dissipation and self-heating problem, which gives better accuracy. The operating range of solid state temperature sensor minus 50 degrees Celsius to 150 degrees Celsius. A good thermal contact is 1 to 5 seconds and poor thermal contact 60 to more seconds, and dissipation constant 2 to 20 millivolt per second. and their applications, consumer and industrial application, interface to control system and computer, to provide an automatic reference temperature and compensation for a thermocouple. Now we have to use a different temperature scale. So the scale may be differ in two ways. The point chosen 0 degree and select convenient incremental units or degree on the scale. The temperature scale are differ on boiling point and freezing point of water, both at sea level atmospheric pressure. So Kelvin, first reference point is absolute temperature 0 Kelvin. Second reference point is a triple point of water 273.16 Kelvin at sea level atmospheric pressure, that is the used for scientific application. Second one is the Celsius. Degree Celsius is the freezing point of water and 100 degrees Celsius is the boiling point of water, both at pressure of 1 standard atmosphere, commonly used in a measurement. Fahrenheit, water freezes at 32 degree Fahrenheit and boils at 212 degree Fahrenheit at sea level atmospheric pressure, mostly used in United States, are commonly used. So following table shows the conversion of temperature scale. So first one is the Fahrenheit to Kelvin and Celsius, second one is the Celsius to Fahrenheit and Kelvin is the Celsius to Fahrenheit. So that gives the formula how to convert one scale to the another scale. Now next one is the motion sensor. It is designed to measure the rate of change of position, location or displacement of an object. The position of an object as a function of time is x of t. Then first derivative gives the speed of object v of t, velocity if direction specified. The speed of object is also changing, then first derivative of the speed gives the acceleration v of t d of t upon dt. Second derivative of the speed gives the acceleration a of t is equal to d of t upon dt, d square xt upon dt square. Accelerometer is motion sensor which can be determine speed, that is the velocity, acceleration and position of the object. So Vt is equal to V of 0 plus 0 to t at dt, and x of t is equal to x of 0 plus integration of 0 to t V of t. So acceleration is a is equal to meter per second square, speed is velocity meter per second, position m, and gravity g 9.8 meter per second square. Now next concept is the types of motion. When design of sensor to measure motion is often tailored to the type of motion that is to be measured. First one is the rectilinear. This type of motion is characterized by velocity and acceleration which composed of straight line segments. The objects may accelerate forward to a certain velocity and deaccelerate to stop, reverse and so on. Typically maximum acceleration are less than a few gs and little angular motion in a curved line is allowed. If there angular motion, then several rectilinear motion must be used is sensitive to only one line of motion. Example, vehicle motion, one transducer for forward direction of vehicle and another for perpendicular to the forward axis of the vehicle. And second one is the angular, it measures only rotation about the same axis. Example, shaft of the motor, it cannot be measure the physical displacement of the whole shaft but only its rotation. Third one is the vibration, it measures the magnitude of acceleration. A object placed in a periodic motion some equilibrium position which very large peak acceleration may reach to 100 gram or more. This motion known as vibration. Example, rocket launching involve acceleration 1 to 10 g. Vibration are somewhat random in both the frequency of periodic motion and the magnitude of displacement for equilibrium. In normal daily living, a person rarely experiences acceleration that vary 1g by more than few percent. Next one is the shock. A special type of acceleration occurs when an object that may be uniform motion or modestly accelerating is suddenly brought to rest as in a collision. Such phenomena are the result of very large acceleration or actually deceleration, as when an object is dropped from some height onto a hard surface. This is shock given to a deceleration that are characterized by very short times in milliseconds. Next one is the accelerometer principle. There are several physical processes that can be used to develop a sensors to measure acceleration. In the industrial world, however, the most common design is based on the combination of Newton's law of mass acceleration and Hooke's law of spring action. So first one is the Newton's law is simply state that the mass is the undergoing an acceleration A, then there must be force F acting on the mass and given by F is equal to ma. Hooke's law state that if a spring of spring constant K stretched extended from its equilibrium position for a distance del x, then there must be a force acting on the spring given by F is equal to K del x. Now first one is the spring mass system. We have to see the diagram. No acceleration and spring mass system with acceleration. A mass which free to slide on a base. The mass is connected to the base by a spring that is in its unextended state and exerts no force on the mass. The whole assembly is accelerated to the left. Now the spring extends in order to provide the force necessary to accelerate the mass. The condition is described by the equating Newton's and Hooke's law. Ma is equal to K del x, where K is the spring constant in Newton per meter square, del x is the spring extension in meter, m is equal to mass in kg, a is the acceleration in meter per second square. Above equation allow the measurement acceleration to be reduced to a measurement of spring extension linear displacement, because a is equal to k upon m del x. If the acceleration is reversed, then only spring is compressed instead of extended. The mass of the converts the acceleration to stop to spring displacement is referred to test mass and seismic a spring mass principle. Next concept is the natural frequency and damping. On closer examination of the simple principle just described, we find another characteristics of spring mass system that complicates the analysis. In particular, a system consisting of a spring and attached mass always exhibits oscillation at some characteristics natural frequency. If we pull a mass back and then release it in the absence of acceleration, it will be pulled back. The spring overshoot the equilibrium and oscillate back and forth. Only friction associated with the mass and base eventually bring the mass to rest. Any displacement measurement system will respond to this oscillation as if an actual acceleration occurs. This natural frequency is given by Fn is equal to 1 upon 2 pi square root of k upon m. Fn is the natural frequency hertz, k is the spring constant in Newton per meter, and m is the seismic mass in kg. So that diagram shows the time and mass displacement. Now next one is the natural frequency and damping. The friction that eventually bring the mass to rest define the damping coefficient alpha, which has units of per second. In general, the effect of oscillation is known as transient response, described by a periodic damped signal x of xt of t x0 e raised to minus alpha t sine 2 pi fn t. So here xt transient mass position, x0 is the peak position initially, alpha is damping coefficient, fn is the natural frequency. The parameter of natural frequency and damping coefficient have a profound effect on the application of accelerometer. So that diagram shows how to changes their position. Now what happens when the vibration effects on the effect of natural frequency damping on the behavior of spring mass accelerometer is best described in terms of an applied vibration. If the spring mass system is exposed to vibration, the resultant acceleration of the base is given by equation at is equal to minus omega square x0 sin omega t. Above the equation is used in equation ma is equal to k del x. So where W is equal to 2 pi f, f is the applied frequency del x minus mx0 upon k omega square sin omega t. Above spring mass accelerometer has been fixed to a table that is vibrating. The x0 is the peak of the amplitude of the table vibration and del x is the vibration of the systemic mass within the accelerometer. Thus, this equation predicts that the systemic mass vibration peak amplitude varies as the vibration frequency is squared, but linearly with the table vibration amplitude. There is a resonance effect when the table frequency equals the natural frequency Fn of the accelerometer. That is, a del x goes through a peak. The amplitude of the resonant peak is determined by the amount of damping. The systemic mass vibration is described by equation del x only up to about Fn upon 2.5. The types of accelerometer is which depends upon the following factors: range, natural frequency, damping, specification sheets for and mass displacement, spring constant, damping coefficient, scale factor. First is the potentiometer. So this type of accelerometer measures mass motion by attaching the spring mass to the wiper. In this manner, mass position is conveyed as a changing resistance. The natural frequency of these devices is generally less than 30 Hz, limiting their application to steady state acceleration or low frequency vibration measurement. Numerous signal conditioning schemes are employed to convert the resistance variation into a voltage or current signal. Second one is the LVDT. It is a very linear variable differential transformer, and their construction, it is a natural linear displacement. In LVDT, core itself is the systemic mass displacement of the core are converted directly into a linearly proportional AC voltage. The accelerometer generally have natural frequency less than 80 Hz, are commonly used for a steady state and low frequency vibration. Next one is the variable reluctance. This accelerometer types falls in the same general category as the LVDT in that an inductive principle is employed. Here test mass is usually a permanent magnet. The measurement is made under the influence of acceleration. This accelerometer is used in vibration and shock studies only because it has an output only when the mass is in motion. The natural frequency is typically less than 100 Hz. This types of accelerometer often is used in a oil exploration to pick up vibration reflected from underground rock strata. In this form, it is commonly referred to as a geopore. Now next one is the piezoelectric. Here a piezoelectric crystal spring is loaded with a test mass in contact with crystal. When exposed acceleration, the test mass traces crystal by a force F is equal to ma, resulting in voltage generated across the crystal in millivolt. A measure of this voltage is then measure of the acceleration. The crystal R per second is very high impedance source and thus requires a high input impedance and low noise detector. The natural frequency may exceed 5 kHz. It can be used for vibration and shock measurements. Now next one is the application of accelerometer. First one is the steady state acceleration. In this application measures the acceleration that vary in time but that non-periodic. The stop-go motion of an automobile is an example of a steady state acceleration. For steady state acceleration, sensor having adequate range to cover expected acceleration magnitude, a natural frequency efficiently high that its period is shorter than the characteristics time span over which the measured acceleration changes. By using electronic integrator, the basic accelerometer can provide both velocity first integration and position second integration information. Second one is the vibration. The application of accelerometer for vibration first require that the applied frequency is less than the natural frequency of the accelerometer. It must be the stated range of acceleration measured will be never exceed that of the specification for the device. This assurance must come from a consideration of del X equation under circumstance of maximum frequency and vibration displacement. Shock. The primary element of importance in shock measurement are that the device has natural frequency that is greater than 1 kHz and a range typically 500 G. The primary accelerometer that can satisfy this requirement is the piezoelectric type. Next one is the optical sensor. Light is a form of energy which is propagated in the form of electromagnetic waves. These waves are called electromagnetic radiation that are propagated through space. The electromagnetic waves are typically described by the following three physical properties: the frequency f, wavelength lambda, and photon energy E. F is equal to c upon lambda, F is equal to E upon h, E is equal to hc upon lambda. So where c is the speed of light, all wave travels as a speed of 3 into 10 raised to 8 meter per second in a vacuum. H is the 6.626 into 10 raised to minus 34 joule per second, Planck constant. The range of electromagnetic radiation from low frequency to very high frequency is known as electromagnetic spectrum. The electromagnetic spectrum, the entire range of EM waves in order to increasing frequency and decreasing wavelength. The relation between wavelength and frequency and energy are: wavelength is shorter or decreases, then frequency is high or increases, or also energy and high and increases. And when wavelength is longer and increases, then frequency lower and decreases, and energy is lower and decreases. So frequency and energy are same, but wavelength are changes. EM waves are considered to be transfer waves because they are made of vibrating electric and magnetic field at right angles to each other and to the direction the waves are traveling, can travel in a vacuum. They do not need a medium, travel at the speed of light. So there are the different types of waves in a electromagnetic spectrum, and their wavelength range, frequency range, and energy range in terms of meter, wavelength in terms of meter, frequency in hertz, and energy in joules. So like as a radio wave, microwave, infrared wave, optical or visible wave, ultraviolet wave, X-ray wave, and gamma wave, and their wavelength, frequency, and energy range. So that diagram show how to frequency, wavelength, and energy change by indication of that arrow, and this shows the how to bands are generated in a electromagnetic spectrum. Now next one is concept is the optical and photodetector. The optical detector are light sensors or transducer that produce electrical output in response to EM radiation. It is a device in which light from a photon is used to produce electrons for conduction by having the absorbed photon liberate a bound electron. Optical detectors are classified into three classes: photoconductive detector, photovoltaic detector, photoemissive detector. The photodetector characteristics like as a spectral response, the amount of current produced with wavelengths, assuming that all wavelengths are at the same level of light. Next one is the photosensitivity. It is the ratio of light energy in watts incident on the device to the resulting current in amperes. Next one is the quantum efficiency. It is the number of generated electron hole pair, that is current, divided by the number of photons. Next one is the dark current. It is the amount of current that flows through the photodiode in the absence of any light. Dark when the diode is reverse biased. This is a source of noise when the diode is reverse biased. Next one is the cutoff frequency. It is the highest frequency wavelengths at which the photodetector is sensitive. Next characteristics is the forward bias noise. It is a current source of noise that is related to the shunt resistance of the device. The shunt resistance is defined as the ratio voltage near 0 volt to the amount of current generated. Noise equivalent power is defined as the amount of light of a given wavelength that is equivalent to the noise level of the device. The terminal capacitance is a capacitance from the PN junction of diode to the connectors of the device. It limits the response of photodetector. Next one is the timing response. It is the time for the output signal to climb from 10 to 90% of its amplitude rise time and to drop from 90 to 10. It is the fall time. Next one is the frequency bandwidth. It is the frequency or wavelength range in which the photodetector is sensitive. Next one is the photoconductive detector. The conductivity of semiconductor material changes with intensity of incident of radiation. Theory: the photon of incident radiation is absorbed by the semiconductor material. The electron from the valence band get excited. If energy of incident photon is sufficient, electron jumps from valence band to conduction band. Therefore, number of conduction electrons increases due to incident EM radiation. The number of electrons excited depends on number of photons absorbed, that is depend upon intensity of incident radiation. The photoconductive detector: to jump electron from valence band to conduction band, the incident photon must have minimum energy equal to band or energy gap of the semiconductor material. E minimum is equal to HV. Band gap energy is equal to del omega G. So HC upon lambda, that is the del omega G. Lambda max is equal to SC upon del omega G, or Vmax is equal to del omega G upon H. Any radiation having wavelength greater than for frequency less than cannot be causes any resistance change in the semiconductor. Materials whose resistance or conductivity is function of incident radiation are called photoresistive or photoconductive materials. Devices operate on the principle known as photoconductive cell. Next one is the photoconductive cell. The material like cadmium sulfide, so shows in a diagram how to conduct photoconductive cell generated, that is CDS, having energy gap is 2.44 electron volt, and cadmium selenide CDSE with energy gap 1.74 eV are used to constant the photoconductive cell. These materials have large energy gaps, so they very high resistance at room temperature. The resistance at photoconductor in absence of EM radiation is known as dark resistance, and it varies from the few hundreds ohm to several mega ohm for different types of photoconductor. It also called light dependent resistors, LDR. Its resistance varies with temperature, so it is operated in limited temperature range. Its response non-linear. It measures change in resistance. Simple bridge circuit are used to convert the change in resistance into a voltage or current signal. Op-amp circuit are used. So that is the diagram is of photoconductive cell. Now next one is the photodiode detector. A photodiode detector can be operated in one of two modes: photoconductive reverse bias, photovoltaic reverse bias. Mode of selection depends upon the application's speed requirement and the amount of tolerable dark current, that is the leakage current. Photoconductive, higher dark current. If photoconductive mode, an external reverse bias is applied, which is the basis for our DET series detector. The current measured through the circuit indicates illuminance of the device. The measured output current is linearly proportional to the input power. Applying a reverse bias increases the width of the depletion junction, producing an increased responsively with a decrease in junction capacitance, and produces a very linear response. Second one is the photovoltaic. In this mode, the photodiode is zero biased. The flow of current out of this device is restricted and a voltage builds up. The mode of operation exploits the photovoltaic effect, which is the basis of solar cell. The amount of dark current is kept at a minimum when operating in a photovoltaic mode. A dark current is a leakage current that flows when a bias voltage is applied to a photodiode. A photoconductive mode, higher dark current, doubles the dark current for every 10 degrees Celsius, and it doubles the shunt resistance every 6 degrees Celsius. Applying a higher bias will decrease the junction capacitance but will increase the amount of dark current present. Next one is the photovoltaic detector. The potential difference develops across the PN junction when it's illuminated with EM radiation. It is converts EM energy, electromagnetic energy, into a electrical energy. So construction and working of photovoltaic cell. A photovoltaic cell is a giant diode constructing PN junction between appropriately doped semiconductor. Photon striking the cells passes through the thin p-doped upper layer and is absorbed by electrons in the lower n layer, causing formation of conduction electrons and holes. The depletion zone potential of the PN junction then separates these conduction holes and electron, causing potential difference across the junction. So that is the photovoltaic solar cell. The open circuit voltage V developed in the cell varies logarithmically with the radiation intensity by V is equal to V0 log EI, where V is the unloaded output voltage, V0 is the calibration voltage constant, I is the intensity at radiation. The materials used for photovoltaic cell are silicon, selenium, germanium, indium arsenide, indium antimonide. Simple op-amp circuits can be used to measure the open circuit voltage or current at a specified load current. The advantages are very fast. It generates voltage without any external bias, that is the active transducer. The disadvantages of this detector is the low output and it is the costly. So here is some radiation bombarded on the p-doped semiconductor. So there is the junction and you will get the desired output. Next one is the photodiode detector. A photodiode is a type of photodetector capable of converting light into either current or voltage depending upon the mode of operation. The photodiode are similar to regular semiconducting diode, except that they may have either exposed to detect vacuum UV or X-ray, or packaged with a window or optical fiber connection to allow light to reach the sensitive part of the device. Many diodes designed for use specifically as a photodiode will also use PIN junction rather than PN junction. The photoemissive detector and their principle are some photosensitive material like sodium, potassium illuminated with suitable radiation, then emission of electrons take place from the surface of material. This effect is known as photoelectric effect. Devices work on photoelectric effect are called as photoemissive detector. Example, photocell. It is a device which converts electromagnetic energy into electrical energy. It consists of two electrodes, cathode and anode, enclosed in an evacuated glass bulb mounted on a non-conducting base. The anode is in the form of rod. Anode and cathode are connected to two pins at the bottom of base, which are used for external connection. Next is the photocell, a simple photocell which cathode is kept at negative potential and anode is at positive potential. When the cathode is illuminated with suitable radiation, electrons is emitted. These electrons are attracted by positive charge anode so that photoelectric current flows through the circuit. The photocurrent increases with increasing intensity of EM radiation. The advantages are good stability and long life. The disadvantages are slow sensitivity and very low output for vacuum tube cell. The sensitivity and output current can be increased using gas fitted tubes or using photomultipliers. So that is the diagram shows how to photocell construct. Next one is the photomultiplier cell. It consists of number of electrodes are known as diode. Diode are maintained at successively more positive potential. The final electrode is anode, which is at highest positive potential. Photosensitive cathode is illuminated with suitable radiation which emits photoelectrons. These photoelectrons are accelerated by the first diode. This electron strikes first diode with sufficient energy so that several electrons are rejected from its surface. This phenomenon is known as secondary emission. All these electrons are efficient energy to again reject several secondary diodes, where each strikes the surface with sufficient energy to again eject several secondary electrons. The advantages are high output, good sensitivity. The disadvantages are needs very high potential and very large size and expensive. So that is the construction of photomultiplier tube. Next one is the optical source. To operate optical sensor, electromagnetic radiation sources are necessary. There are many EM sources are developed, like as a incandescent source, atomic source, fluorescent source. The above sources have following drawbacks, like as a incoherent, divergence, not particularly monochromatic. The complicated lens are required to coverage the rays. Heat dissipation is expensive. Wavelength characteristics. Above these problems, a highly coherent, monochromatic and very little divergence is developed, is known as a laser. So it is the light amplification by stimulated emission of radiation. For light generation, it is possible using HENE or semiconductor laser. The process of generation of laser EM radiation is possible when following conditions are satisfied. First one is the population inversion. Normally valence band is more heavily populated than the conduction band. For laser action, conduction band is to be more populated than valence band. This situation is known as population inversion. To create population inversion, very high density forward current is passed through a small active area. Second one is the stimulated emission. So diagram shows how to stimulated emission generated and spontaneous emission generated, and what is the positive feedback in figure B. So when an atom electrons jump to lower energy states on its own, then it emits a photon, such known as the spontaneous emission. If a photon is incident on a excited atoms or electron de-excited, so incident photon stimulated the atoms or electron jump from the high energy state to low energy state. This process, a photon is emitted. The photon emitted due to interaction between incident photon and excited atoms is known as stimulated emission. The emitted photon has exactly the same energy, phase and direction as the incident. Now next one is the positive feedback. Using mirror at the end of active layer of positive feedback can be obtained when the incident photon stimulate atom or electron to jump lower energy level, a photon emitted. Therefore these are two photons, one external and other stimulated. These two photons are reflected back from the mirror at one end. These two photons work as external photon and stimulate other two atoms, so that other two photons are emitted. Now there are four photons. Other mirror again reflects these four photons and they works as an external photon stimulation. In this way, two mirrors are used to increase the photon is known as positive feedback. The second mirror is partially polished, so a fine beam of stimulated photon beam emerges. Next one is the laser diode. It can be constructed using semiconductor material like as a gallium arsenide. Gallium arsenide has very high refractive index, above 3.6, more than 30% of incident photons are reflected back at gallium arsenide air interface. That is, the interface act as a partially polished mirror. Electron holes are injected by forward current into a active area where they recombine the recombination results in the radiation photon. Next one is the application of photosensor is the optocoupler. It is a optoisolator. It consists of LED and photodiode. So diagram shows LED and photodiode. So when optical source LED is operated, light is emitted from the light from LED incident on photodiode, and it sets the reverse current through the resistance R2. The isolation resistance of the order of 10⁻11 ohm. Advantages of optoisolator is very high isolation resistance, high operating frequency up to 10 kHz, no effect of EM or electrostatic field, small size, maintenance free, more lifetime, no effect of vibration. Next one is the application of photosensor is label inspection. So see the diagram how to inspect the label of atom or object. When large number of items are produced batch wise, it is possible to label each and every items manually. So atomic process are used to attach the label. Inevitably some atoms are without labels or labels are incorrectly attached. Label inspection is used to examine presence of label and alignment label on products. Detect the presence of label and alignment of label. Optical source and optical sensors are used when product passes from control room, which consists of optical source and photodetector. The form of optical source is reflected from the label and is reflected light falls on the optical sensor. The size of label, message in a label, all these details are available in control system. The signal from photodetector is compared with store information in control system if signal from photo detect. Third one application is ranging. The position or speed of object can be determined using range finder, which consists of laser source, photodetector, light source emits which reflected from the object, which detect the position determined. Reflected light is detected by a photodetector. The time interval between emitted light and received light is the total time required to cover the twice distance between rangefinder and object. D is equal to Ct upon 2, where T is the total time taken light pulse. C is equal to speed of light or velocity of light, 3 into 10 raised to 8 meter per second, and D is the distance. Next application is the turbidity. One of the many characteristics of liquid involved in the process industry is known as the turbidity. Turbidity refers to the lack of clarity of liquid, which can be caused as a suspended particulate material. Turbidity can be indication of a problematic condition because of impurities or improperly dissolved products. It can also be intentional, as example when some material suspended in liquid for ease of transport these pipes. Turbidity can be measured optically because it affects the propagation of light through the liquid. Example to measure the turbidity of liquids in process in light. Next one is the pyrometry. Pyrometer is a non-device that intercepts and measures the thermal radiation, a process known as pyrometry. This device can be used to determine the temperature of an object surface. It is a non-contact device, a device that measures the thermal radiation in the temperature range. A pyrometer has an optical system and detector. The optical system focuses the thermal radiation on the detector. The output signal of the detector, temperature T, is related to the thermal radiation, EM radiation, EM emission, and heat absorption. One important note: thus interplay between the electromagnetic radiation emission and heat absorption by an object in achieving the thermal equilibrium. Next one is the black body radiation. Assume that the ideal object is now placed in thermal equilibrium so that its temperature is controlled. At low temperature, EM radiation emitted predominantly in the long wavelength, far infrared to the microwave range. The high temperature EM radiation maximum emitted radiation in the shorter wavelengths near visible band. An object glow as its temperature increases. For the black body, the temperature and emitted radiation are in 1:1 corresponds in the following respect. The total radiation is a study of black body radiation shows that the total emitted radiation energy per second for all wavelength increases with the fourth power of the temperature, E directly proportional to T raised to 4, where E is the radiation emission in joule per second per unit area, watt per meter square, and T is the temperature in Kelvin of object. Next one is the monochromatic radiation. The radiation energy emitted at particular wavelength increases as a function of temperature. Joule per second per area at some given wavelength increases with temperature. This is manifested by the object getting brighter at the same wavelengths as its temperature increases. Next one is the black body approximation. Most materials emits and absorb radiation at preferred wavelengths given rise to color, so that these objects cannot be displayed like as an ideal black body curve. Correction factors are applied to relate the radiation curve of real object to that an ideal black body. The radiation emitted from a small hole in a metal enclosure is close to an ideal black body. For calibration purpose, a black body constructed. Next one is the broadband parameter and their construction. One type of temperature measurement system based on a emitted EM radiation used to relation between the total emitted radiation energy given temperature. The total electromagnetic energy emitted for all wavelengths expressed as a joule per second per unit area varies with the fourth power of the temperature. A system that responded to this energy could thus measure the temperature of the emitted object. It is virtually impossible to build a detection system to respond to radiation of all wavelengths so that the most of the energy is carried in the IR and visible bands of radiation, and collection of radiation energy in this band provides good approximation of the total radiated energy. Next one is the total radiation parameter. So that diagram shows how to total radiation parameter determines the object temperature by input radiation of broadband of wavelengths. One type of broadband parameter is designed to collect radiation extending from the visible through the infrared wavelength and is referred to as a total radiation parameter. The radiation from an object is collected by the spherical mirror as focused on the broadband detector D. The signal from this detector then this is a representation of the incoming radiation intensity and thus the object temperature. In these devices, the detector is offered a series of micro thermocouple TC and attached to a blackened platinum disc. The radiation absorbed by the disc which heats up and result in an EMF developed by thermocouple. The advantages of such a detector is that it responds to a visible and IR radiation with little regard to wavelength. Next one is the broadband pyranometer, that is the IR pyrometer, infrared pyrometer. Another popular version of the broadband pyrometer is one of the mostly sensitive to IR wavelengths. This device is often uses a lens from silicon or germanium to focus the IR radiation on suitable detector. IR parameters are often handheld pistol-shaped device that read the temperature of an object toward which they are pointed. Characteristics are it often have readout directly in temperature, either analog and digital, depending on cost, stable range 0 to 1000 degrees Celsius with accuracy plus minus 5 to plus minus 0.5 degrees Celsius. Accurate measurement required the input of emissive information by variation in a reading scale factor. Such correction factor accounts for the fact that an object is not ideal black body and does not confirm exactly the radiation curve. Now next one is the applications. First one, the metal production facility. Many industrial application work as excess of 5 degrees Celsius are common. Contact temperature measurements usually involve a very limited lifetime for the measurement element. With broadband parameter, however, a non-contact can be made and the result converted into a process control loop signal. Second one is the glass industry. It is the very high temperature control in the production, working and handling of glasses. The broadband parameter design process control system for glass furnace temperature have been regulated with plus minus 0.1 K. Semiconductor process. It is used for carefully regulate induction heating, high temperature processes producing pure crystal, crystal pull rates and other related parameters. IR parameter is improve accuracy below than 500 Kelvin temperature range. Next one is the narrowband parameter. Another class of parametry depends on the variation of monochromatic radiation energy emission, the temperature. These devices often are called optical parameter because they generally involve wavelengths only in the visible part of the spectrum. We know that intensity of one object is matched to the another. The temperature are the same. In the optical parameter, the intensity of a heated platinum filament is varied until it matches an object whose temperature is to be determined. Because the temperature are now the same and filament temperature is calibrated versus a heat setting the temperature, the system is focused on the object whose temperature is to be determined. The filter pick up out the desired wavelength, that is the red. The viewer also sees the platinum filament superimposed on the image of the object. So that is the construction of the narrowband parametry. An optical parameter match the intensity of the object to heated calibrated filament. Comparison is made red filter. Now at low heating filament appears dark, see the diagram. At high heating filaments appears bright, and adjusting heating some part of the filament are invisible. The range of optical parameter determined at low endpoint by object becomes visible in the red 500 Kelvin and virtually limited by the melting point of platinum at the upper end 3000 Kelvin. Accuracy is typically plus minus 5 to plus minus 10 K. Application predominantly in spot measurement. So this diagram gives the how to filament heating and their filament appears. Thank you.